Achieving a high score on the Master Electrician Exam requires dedicated preparation and a solid understanding of electrical principles and codes. It's great when someone succeeds in their efforts. Mastering the Master Electrician Exam involves several key areas. Firstly, thoroughly understand the National Electrical Code, or NEC. The NEC is the foundational document for electrical installations, and a deep understanding is crucial. Focus on the articles and sections most relevant to the exam, such as those covering wiring methods, overcurrent protection, grounding, and equipment installation. Secondly, practice with sample questions and exams. Familiarize yourself with the types of questions asked in the format of the exam. Practice tests help you identify your strengths and weaknesses, allowing you to focus your study efforts on areas where you need improvement. Thirdly, take a comprehensive review course. A good review course provides structured learning, expert instruction, and valuable insights into the exam. Look for courses that cover all the essential topics and offer ample opportunities for practice and review. Fourthly, review electrical theory and calculations. A strong grasp of electrical theory is essential for understanding the principles behind electrical installations. Brush up on topics such as Ohm's law, Kirchhoff's laws, series and parallel circuits, and power calculations. Fifthly, understand blueprint reading and electrical symbols. The ability to interpret electrical blueprints is essential for visualizing and understanding electrical systems. Familiarize yourself with common electrical symbols and how they are used in blueprints. Sixthly, focus on specific areas of the NEC. Certain areas of the NEC are more heavily emphasized on the Master Electrician Exam. These areas include grounding and bonding, overcurrent protection, wiring methods, and equipment installation. Seventhly, manage your time effectively during the exam. Time management is critical for completing the exam within the allotted time. Practice pacing yourself during practice exams and develop a strategy for answering questions efficiently. Eighthly, stay calm and focused during the exam. Test anxiety can negatively impact your performance. Practice relaxation techniques and stay calm and focused during the exam. Read each question carefully and take your time to answer it accurately. Ninthly, review your answers before submitting the exam. If time permits, review your answers before submitting the exam. Look for any errors or omissions and make any necessary corrections. Tenthly, familiarize yourself with common electrical formulas. Electrical formulas are essential for performing calculations related to voltage, current, resistance, and power. Memorize common formulas such as Ohm's law, power formulas, and voltage drop formulas. Some example electrical calculations include the following. Ohm's law, which states that voltage E is equal to current I multiplied by resistance R, or E equals I times R. This formula is used to calculate voltage, current, or resistance in a circuit. Power formulas, which relate power P to voltage E and current I. The basic power formula is P equals E times I. This formula can be rearranged to calculate power, voltage, or current in a circuit. Voltage drop formulas, which are used to calculate the voltage drop in a conductor due to its resistance. The voltage drop depends on the conductor's length, current, and resistance. The formula for voltage drop is voltage drop equals 2 times K times L times I divided by circular mils, where K is the direct current constant for the conductor material, L is the one-way length of the circuit in feet, I is the current in amps, and circular mils is the area of the conductor in circular mils. Single-phase power calculations, which involve calculating power, voltage, and current in single-phase alternating current circuits. The power formula for single-phase alternating current circuits is P equals E times I times power factor, where power factor is the ratio of real power to apparent power. Three-phase power calculations, which involve calculating power, voltage, and current in three-phase alternating current circuits. The power formula for three-phase alternating current circuits is P equals square root of 3 times E times I times power factor. Conductor ampacity calculations, which involve determining the maximum current carrying capacity of a conductor. The ampacity of a conductor depends on its size, insulation type, and ambient temperature. Ampacity values are listed in NEC Table 310.15b16. Conduit fill calculations, which involve determining the maximum number of conductors that can be installed in a conduit. Conduit fill is limited by the NEC to prevent overheating and damage to conductors. Short-circuit current calculations, which involve calculating the maximum short-circuit current that can occur in an electrical system. Short-circuit current calculations are used to select appropriate overcurrent protection devices. Ground fault current calculations, which involve calculating the ground fault current that can occur in an electrical system. Ground fault current calculations are used to design effective grounding systems. Motor starting current calculations, which involve calculating the high inrush current that occurs when a motor starts. Motor starting current calculations are used to select appropriate motor starters and overcurrent protection devices. Transformer calculations, which involve calculating voltage, current, and power relationships in transformers. Transformer calculations are used to select appropriate transformers for specific applications. Lighting calculations, which involve calculating the amount of light needed for a particular space. Lighting calculations take into account factors such as room size, surface reflectance, and task requirements. In addition to these formulas, it is also important to understand the NEC requirements for conductor sizing, overcurrent protection, grounding, and bonding. By mastering these formulas and NEC requirements, you can improve your understanding of electrical systems and perform accurate calculations for a variety of applications. Regarding grounding and bonding, it is important to understand that grounding and bonding are critical safety measures in electrical systems, designed to protect people and equipment from electrical shock and fire hazards. Grounding provides a low impedance path for fault current to return to the source, allowing overcurrent protection devices to quickly trip and clear the fault. Bonding ensures that all metallic parts of an electrical system are electrically connected, creating a common ground potential and preventing voltage differences that could cause shock hazards. The NEC contains detailed requirements for grounding and bonding, including conductor sizing, electrode requirements, and bonding methods. Some key grounding and bonding concepts include the grounding electrode system, which consists of electrodes such as ground rods, ground plates, and metal water pipes that are used to connect the electrical system to the earth. The equipment grounding conductor, or EG, which is a conductor that provides a low impedance path for fault current to return to the source. The bonding jumper, which is a conductor that connects metallic parts of an electrical system to ensure electrical continuity. Ground fault circuit interrupters, or GFCIs, which are devices that detect ground faults and interrupt the circuit to prevent electrical shock. Important NEC articles related to grounding and bonding include NEC Article 250, which covers the general requirements for grounding and bonding. NEC Article 250.24 covers grounding of alternating current systems. NEC Article 250.30 covers grounding of separately derived systems. NEC Article 250.50 covers grounding electrode systems. NEC Article 250.92 covers bonding of equipment. NEC Article 250.118 covers types of equipment grounding conductors. NEC Article 250.130 covers equipment grounding conductor connections. NEC Article 250.134 covers equipment grounding for fixed equipment. Regarding overcurrent protection, it is crucial to understand that overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. These devices interrupt the flow of current when it exceeds a safe level, preventing damage to equipment and reducing the risk of fire. The NEC contains detailed requirements for overcurrent protection, including conductor sizing, device selection, and coordination. Some key overcurrent protection concepts include ampacity, which is the maximum current carrying capacity of a conductor; overload, which is a condition where the current in a circuit exceeds its rated ampacity; short circuit, which is a condition where there is a low resistance path between two conductors, resulting in a high current flow; Circuit breaker, which is an overcurrent protection device that automatically interrupts the circuit when an overcurrent condition occurs. Fuse, which is an overcurrent protection device that contains a fusible link that melts and interrupts the circuit when an overcurrent condition occurs. Time current curves, which are graphical representations of the time it takes for an overcurrent protection device to trip at different current levels. Selective coordination, which is the practice of coordinating overcurrent protection devices to ensure that the device closest to the fault trips first, minimizing the impact on the rest of the electrical system. Important NEC articles related to overcurrent protection include NEC Article 240, which covers the general requirements for overcurrent protection. NEC Article 240.4 covers protection of conductors. NEC Article 240.6 covers standard ampere ratings for fuses and circuit breakers. NEC Article 240.15 covers the location of overcurrent protection devices. NEC Article 240.21 covers overcurrent protection for tap conductors. NEC Article 240.85 covers overcurrent protection for specific types of equipment. NEC Article 240.87 covers the coordination of overcurrent protection devices. Regarding wiring methods, it is essential to grasp the various wiring methods used in electrical installations, each with its own set of requirements and applications. Wiring methods include conduit, cable, and other wiring systems used to route and protect electrical conductors. The NEC contains detailed requirements for wiring methods, including conductor sizing, support requirements, and installation methods. Some key wiring method concepts include conduit, which is a rigid or flexible metal or plastic tube used to protect electrical conductors. Cable, which is an assembly of two or more conductors enclosed in a protective sheath. Non-metallic sheath cable, or NM cable, which is a type of cable commonly used in residential wiring. Metal-clad cable, or MC cable, which is a type of cable that has a metal sheath for added protection. Underground feeder and branch circuit cable, or UF cable, which is a type of cable designed for underground installations. Electrical metallic tubing, or IMT, which is a thin-walled metal conduit. Rigid metal conduit, or RMC, which is a thick-walled metal conduit. Liquid-tight flexible metal conduit, or LFNC, which is a flexible metal conduit that is liquid-tight. Important NEC articles related to wiring methods include NEC Article 300, which covers the general requirements for wiring methods. NEC Article 310 covers conductors for general wiring. NEC Article 312 covers cabinets, cutout boxes, and meter socket enclosures. NEC Article 314 covers outlet, device, pole, and junction boxes, conduit bodies, fittings, and handhole enclosures. NEC Article 320 covers armored cable. NEC Article 330 covers metal-clad cable. NEC Article 334 covers non-metallic sheath cable. NEC Article 344 covers rigid metal conduit. NEC Article 348 covers electrical metallic tubing. NEC Article 350 covers flexible metal conduit. NEC Article 352 covers rigid polyvinyl chloride conduit. NEC Article 356 covers liquid-tight flexible non-metallic conduit. NEC Article 358 covers electrical intermediate metal conduit. Regarding equipment installation, understand that the proper installation of electrical equipment is essential for ensuring safety and reliability. The NEC contains detailed requirements for equipment installation, including mounting requirements, clearance requirements, and wiring connections. Some key equipment installation concepts include grounding, which is the connection of electrical equipment to the earth to provide a low impedance path for fault current. Bonding, which is the connection of metallic parts of electrical equipment to ensure electrical continuity. Clearance, which is the minimum distance required between electrical equipment and other objects. Working space, which is the space required around electrical equipment to allow for safe access and maintenance. Ventilation, which is the provision of adequate airflow to prevent overheating of electrical equipment. Overcurrent protection, which is the use of circuit breakers or fuses to protect electrical equipment from overloads and short circuits. Disconnecting means, which is a device used to disconnect electrical equipment from the power supply for maintenance or repair. Important NEC articles related to equipment installation include NEC Article 110, which covers the general requirements for electrical installations. NEC Article 400 covers flexible cords and cables. NEC Article 404 covers switches. NEC Article 406 covers receptacles. NEC Article 408 covers switchboards and panel boards. NEC Article 430 covers motors, motor circuits, and controllers. NEC Article 440 covers air conditioning and refrigerating equipment. NEC Article 450 covers transformers. By thoroughly understanding these key areas and dedicating time to study and practice, you can increase your chances of success on the Master Electrician exam.